Hello everyone, we're starting part 9 today. Part 9 is on rotational kinematics, so the description of rotational motion of objects. So far we looked at the translational motion of objects. Objects that would only move, for example, all at once, that were rigid bodies, for example this small plastic cup thing, and when for example, it was moving in kinematics at the beginning of the semester, all of it was moving at the same time, up or down, and all of it was moving in a circle, in uniform circular motion at the same time. When forces were applied to it, it would apply to all of the points to accelerate all of the points of this thing at the same time. Starting now, this is no longer going to be the case. We're going to need to consider the fact that matter is distributed in space, takes literally space to be where it is. So for example, you can do the same thing with your phone on the table or with a small box or whatever you have. If I take my finger and I push on this cup thing with a magnet here, it just tends to rotate. If I push here, it also tends to rotate. And in both cases, it doesn't translate as we would expect when we have a force acting on an object. To have that result, I need to apply my force in a specific point or aligned with a specific point, right about here. There we go. See, it's not perfect. You can do this more easily by taking 2 points on either side and there we go. This is easier. So in both those two cases, whether I had one finger here or 2 fingers here, what I was doing essentially is putting a force on what's called the center of mass of the object. The center of mass of an object is the point of an object that will move as though all of the system's mass, all of the object's mass were concentrated in that point. And if external forces are applied there, this is what we would observe. So the definition from the notes, totally not reading, is for a system of particles, which an object like this is, the center of mass is the point that moves as though, 1, all the system's mass were concentrated there and all external forces are applied there. When we talked about stuff moving, accelerating, receiving forces before, we were always assuming that all of the mass of the object was concentrated at the center of mass, or that all of the points were moving with the center of mass. We were ignoring the physical properties, the size of the object. Here, that's no longer the case. We can't do that anymore. Going back to the example of my finger pushing, this is a force through the center of mass. This isn't. Now we're going to look at this bit here. If you have only 2 particles, this is how you mathematically find the center of mass. We have here 2 particles, 1 and 2. 1 has a mass m1, 2 has a mass m2. 1 is at position x1, 2 is at position x2. I'm considering only the one-dimensional case here. We can do the same thing in 2 and 3 dimensions, we'll see that after. The center of mass will be somewhere in between. Center of mass, COM. The position of the center of mass is given to you by position of the center of mass is the product in between the position and mass of object 1, of particle 1, plus the product of the object's position and mass of particle 2, divided by the sum of the masses. If you wish, it's a kind of weighted, no pun intended, it's really the word, a kind of weighted average of the mass of the system of 2 particles. If mass 1 is much more massive than mass 2, then this term will have a bigger influence and will bring the center of mass closer to it. If, on the contrary, mass 2 is bigger, then it will bring the center of mass closer to it. If the 2 are exactly equal, the 2 have an equal contribution, the center of mass is exactly in the middle. But also that this doesn't care where the 2 particles are on the x-axis. It just cares about what their respective distance is. The center of mass will always be in between those 2 things. We can have the 2 masses here, we can have mass 1 at the origin and mass 2 on the right, you can have mass 2 at the origin and mass 1 on the left, and the center of mass will always be at the same distance from 1 in those 3 cases. And of course at the same distance from 2 in those 3 cases. Here these x's mean the position with respect to 0. For in one dimension, we just have the position in x. Could be in y, could be in z, you just change the x's for y or z depending on which axis they are. You have 2 dimensions, say on the xy plane, like this board. What you'll have is the coordinates of the points, x and y, for point 1 and point 2. For example, this. You have 2 points, 2 masses, x1, y1, x2, y2. In 2 dimensions, the center of mass is also a point in 2 dimensions. It has coordinates in x and y. So you can find these by using the same formula in x and in y. And then you can extend this. If you were in 3 dimensions, you would have a third equation in z, and it's the same thing. That's only for 2 particles. But what if we have many? If we have many, we just add terms to the 2 sums. So if we have n particles, for example, I'll just write in 1 dimension. You can just change the variables, and the equations are in the notes, but you can just change the variables x for y or z, and you'll get the 2 and 3 dimension versions of this thing. For n particles, where n is some number, assume greater than 2, the position of the center of mass is x1m1 plus x2m2 plus x3m3 plus blah 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 plus xnmn, all of that over m1 plus m2 plus m3 plus blah 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 plus mn, which is summarized here by 1 over big M. Big M is the sum of the small masses and the sum of the product xi and mi. I being just a subscript that you increment. And in a nutshell, this is the center of mass.